Today we are going to talk about viscosity. So viscosity is a critical parameter when we're talking about polymers. We're going to get into kind of several cool equations and regimes. Specifically, we're going to talk about the Einstein-Stokes equation. So it's going to talk a little bit about fluid mechanics. If there's anything that you should remember from fluid mechanics, or at least as a polymer physicist, this is kind of a really kind of important and critical equation, which is basically your viscous drag or your Stokes drag force, which is just going to be, hopefully if you remember this, or hopefully this is covered in basically mechanics. So the force of your viscous drag is going to be 6 pi times your viscosity times radius of your sphere times the velocity at which it falls. But anyways, we'll get more into this later. So we're going to identify some kind of unique and cool properties of polymers like we just introduced in the video the other day. So we saw in our kind of video we introduced into class, you can watch this online. It's El Hormiguero. It's basically the anthill. It's this kind of science TV show, I believe in Spain. But anyways, we saw them run across this material. So at high strain rates, it behaved like an elastic material. If our strain rates are high, if our strain rates were low, we saw that it behaved like a viscous fluid. So the reason why, or the fundamental and physical reason why we get these different behaviors is because in polymers, depending on our scenario, depending on the situation, depending on the perturbation, depending on the state of our polymers, we could either be in these two different regimes, the non-draining or the freely draining regime. So we're going to discuss that in this lecture. We're going to look at specific intrinsic viscosity and then figure out a way, a graphical way, in doing an experiment where we could figure out, okay, what type of solvent do we have? Do we have a good solvent? Do we have a bad solvent? Just from a series of viscosity measurements and molecular weight measurements. So it's going to be a pretty cool kind of application-focused lecture, and the same thing for lecture 6 and 7 as well. Anyways, we've done a lot of theory in this course so far, but now we want to measure properties of our polymers. So we've talked about molecular weight, end-to-end distance, chi parameter. We want to be able to actually physically measure them. And so now we're going to get into actual techniques. And because a lot of those, molecular weight, chi parameters, basically the size of your chain, it affects properties like basically the cross-linked, actually this is non-cross-linked rubber elasticity, shear thickening, that is not a typo. Anyways, elastic modulus for cross-linked networks. Again, lots of different polymer properties depend on molecular weight or chi or your root mean squared end-to-end distance. So it's critical that we're able to measure these values and these properties. So today we're going to focus on basically looking at the viscosity of dilute solutions to figure out the molecular weight of polymers, and then we're going to figure out these different free draining and non-draining regimes of viscosity. So hopefully you remember back from your basically fluid mechanics. So I think everyone should be familiar with viscosity. So peanut butter obviously is more viscous than water, and from your mechanics lecture, I love this. Again, I'm not a fluid mechanics person, but I definitely still remember this expression here. So if we have basically two plates, so I have a fixed plate here, I have a plate here, a fluid in between, I pull at some velocity, I'm going to create kind of this fluid flow or this flow diagram, and I know that my shear stress, tau, so hopefully remember in our tensor notation of stress and strain, get more into this in our mechanics lecture, but hopefully you remember this from other courses. Sigma 1, 3, we're symmetric because we are in equilibrium, not rotating. All these off-diagonal components, so everything that's not this is equivalently a shear stress. We'll get into kind of some of the details anyways. So the shear stress is related to the viscosity, so that is this eta, so this is my viscosity, times my strain rate, the rate at which I pull or strain kind of basically this viscous fluid. And the kind of cool property, hopefully, you've dealt, let's go back here. And this should kind of make sense, right? So if my material is more viscous, if I'm dealing, for example, with peanut butter, if I'm dealing with peanut butter, I'm going to have a larger shear stress, right? My viscosity increase is going to be harder to pull that plate through that fluid. So that's kind of the kind of context of what we're kind of dealing with here. Additionally, hopefully you can, this is also very reminiscent of several different equations. one of which is our Hooke's law. So remember, this only holds for this specific scenario. So when I'm pulling material 1, 2, this is my only stress. So it is very similar to Hooke's law, but again, the only difference is, again, we have a stress, but instead of our Young's modulus, we have viscosity, and instead of strain, we have strain rate. So kind of that's the idea here. So faster strain rate, the larger resistive force, larger viscosity, larger the shear force. So harder to pull, easier to pull a plate through water than through peanut butter. So this relationship holds, and again, everything kind of seems, hopefully familiar, and everything's right in the world. But one of the kind of interesting behaviors that we will see is if this material does it behave like a Newtonian fluid, so or a non-Newtonian fluid. What we mean by that, if our viscous material, if our fluid, if what we're kind of pulling our plate through is a Newtonian fluid, it is not going to depend. So you can see eta, my viscosity, does not depend on the total strain or the total strain rate. So basically, it's a constant. No matter what my strain rate, if I increase my strain rate, so when I use this dot, it's just the time, first time derivative. If I increase or decrease my strain rate, my eta is still equal to like a value of 5, whatever. It is a constant. It is not. Eta is not a function of eta naught. If we're dealing with a Newtonian fluid, if our material or viscous fluid or whatever our material is, if it's a non-Newtonian fluid, basically it's saying that the viscosity eta is going to be a function of my strain rate, and effectively it could either it could basically, if we look at our, it could increase as my eta increases. So in that case, it's a shear thickening fluid, or if it my viscosity could decrease as my strain rate increases, and that's a shear thinning fluid. So you get some cool behavior, just like what we saw, and we're going to demo today in class, just like we saw here. So this material behaved like an elastic solid. It became more viscous as my strain rate increased. So this eta increased as my strain rate decreased. So it became more viscous, and my eta decreased as my strain rate decreased. So this material behaved like a non-Newtonian fluid. My viscosity changed as a function of that basically shear strain rate. And fortunately or unfortunately, again, fortunately, because again, we want to study, interesting and cool behaviors, because again, this is really it's really interesting behavior that, again, just depending on how you change the shear rate, the strain rate of your material, you could change the properties. You'll see, and we'll come back to this in a second, but we're going to see that a lot of times polymers are non-Newtonian fluids. So the viscosity is not a constant quantity, it's dependent on strain rate or total strain. So that's kind of the key takeaway here. And really, you can, at very, very slow rates, as the shear force goes to 0, you basically can see the property of liquids, where solids can practice infinite viscosity, so they will not flow. We're going to talk about a little bit later on in this course that depending on your strain rate, again, at really extreme values, if I pull infinitely slow, I can make a metal behave like a viscous material, a liquid. If I pull infinitely fast, I can make any viscous fluid behave like an elastic solid. So that strain rate dependence is going to be very, very interesting in terms of kind of the mechanical properties. So we're going to create basically these dynamic mechanical testing measurements where you have a plot of your loss modulus, your storage modulus, and you'll have these kind of different curves as a function of frequency, crossover. But anyways, more on that much later on into our mechanics lecture. So polymers are non-Newtonian fluids, so this viscosity is going to change depending on the strain rate. So we are going to kind of look, again, atomistically and zoom in and figure out how does this viscosity dependence on strain rate, where does it originate? What's the physical or fundamental rationale for why this occurs? So we're going to identify and look at some equations and see basically this freely draining regime and non-draining regime and how it correlates to basically this dependence on the state of the material and the viscous drag force that the polymers exhibit, or kind of how the viscosity changes as a function of the state of the polymer. So that's what's coming up next time. So I'll see you all in the next video. We'll talk about the freely draining regime. Let me know if you have any questions. Thanks. Bye.